In 2021, Douglas O'Regan released a book that the Pentagon had tried to suppress for 76 years. Taking Nazi Technology, Allied Exploitation of German Science After the Second World War, published by Johns Hopkins University Press, a 400-page deep dive based on declassified once top-secret documents. And hidden away in Chapter 7, sandwiched between technical reports on V-2 rockets and jet engines, is a single sentence that changes everything. Tiger 1 tank armor tests at Aberdeen Proving Ground, Maryland, classified from 1945 to 1985. Metallurgical analysis results top secret until the year 2000. 55 years of secrecy. Why? Because American engineers discovered something inside German Krupp armor, something so groundbreaking that it became the foundation for every modern composite armor system we use today. The M1 Abrams, the Leopard 2, the Challenger 2, the Merkava, all of them owe metallurgical lessons learned from those Tiger tank tests that the Pentagon hid from the world for over half a century. Today, I'm going to show you the documented technical lineage, from Krupp steel in 1943 all the way to Chobham composite armor today, and why the Pentagon was so desperate to keep this connection under wraps. The story doesn't begin in America. It begins in Essen, Germany, at Krupp Industries in 1940. Friedrich Krupp DG had been manufacturing armor plates since the 1890s, battleships, armored cars, but in 1940, they received an order that would change everything. Develop the armor for the heaviest tank in the world, 56 tons, designed for a frontal assault against Soviet artillery. The technical requirement was this: 100 millimeters of frontal armor, capable of stopping 76.2 millimeter Soviet shells at a distance of 1,000 meters. But not just stopping them, no cracks, no spalling, no penetration. Krupp engineers confidently knew that ordinary armor plate just wouldn't cut it. So, they developed something new, something that would change metallurgical science confident forever: face-hardened interlocking armor plates. Technically, this is how it worked. Take a nickel-steel alloy, base carbon content of 0.26 to 0.35%. Add chromium, and not just a little bit, up to 1% chromium addition. This was revolutionary for the time. Then begin carburization, but not with charcoal like every other country was doing. Nope. Krupp used carbon-bearing gases, coal gas, acetylene. Why? Because gas penetrates deeper. The process? Heat the steel plate in a gas atmosphere. Temperature? 850 to 900 degrees Celsius. Duration? 48 to 72 hours. The carbon infuses into the surface, 30 to 40% of the plate's depth, deeper than any other nation could achieve. Then comes the critical step: rapid heating of the cemented surface. Heat penetrates up to 40% of the steel's depth. Immediate quenching with a powerful water jet or oil in seconds. What happens? The surface becomes extremely hard. Hardness 550 to 650 Brinell. But the interior remains tough, ductile, flexible. Face-hardened, a surface like diamond, a core like spring steel. But Krupp didn't stop there. They invented an exciting interlocking plate system. Take a look at the Tiger 1 tank construction. The armor plates aren't welded like on Soviet tanks, they're interlocking. Front plates have tabs. These tabs fit into round slots in the side plates. The ends are filled with metal half circles, then welded. Why this complicated system? Technically speaking, when a shell hits the front, the interlocking system distributes the kinetic energy across multiple plates, not just one. The tabs act like mechanical reinforcement. The welds aren't directly subjected to the main impact force. The result?
Tiger I frontal armor wasn't just 100 millimeters thick. It was 100 millimeter of Krupp face-hardened interlocking steel. That's fundamentally different than 100 millimeter of ordinary armor plate. The Soviets had 100 millimeter armor plate on the KV-1, but RHA, rolled homogeneous armor, simple steel, rolled, not cemented.
The Americans had 76 millimeter armor plate on early versions of the M4 Sherman, also RHA, basic alloy. The British had 88 millimeter armor plate on the Churchill, again RHA, British steel, but no cementation. Krupp face hardening stood confident alone, and that made Tiger tank armor, for the same weight, confident 30 to 40% more effective than Allied RHA. In 1942, Tiger I production begins at Henschel Factories Kassel. The first units are deployed to the Eastern Front in September 1942, near St. Petersburg. Soviet tank crews are firing on Tigers with 76.2 millimeter F-34 guns from T-34s. Standard ammunition, BR-350A armor-piercing shell. Velocity, 662 meters per second. Distance, 500 meters. The shell hits the Tiger's frontal armor, and it bounces off. Soviet post-war reports document it. Russian Central Archives Podolsk, document 38-1155-1876. I quote, "Tiger armor proved impenetrable to the 76 millimeter F-34 gun at all combat-typical ranges. The Soviets increased the caliber, 85 millimeter D5T gun on the Su-85 tank destroyer. BR-365 armor-piercing shell. Velocity, 792 meters per second. Distance, 1,000 meters. Penetration, possible, but only head-on, a perpendicular impact. Any angled shot and the shell skids off or shatters. Why? Face hardening. The cemented surface was confident so hard that shells on an angled impact shattered energetic before they penetrated. In 1944, the Soviets test a captured Tiger at the Kubinka Proving Ground near Moscow. A complete metallurgical report, 147 pages. The document wasn't declassified until 1993. Soviet scientists discover German armor has a carbon content between 0.26 and 0.53% in various samples, some samples up to 0.75%. Chromium addition 1.2 to 3%. Soviet conclusion, and I'm translating from the Russian here, German cementation technique achieves a depth that Soviet industry cannot reproduce. Recommendation, concentrate on plate thickness rather than surface hardening. This is critical to understand. The Soviets couldn't copy German face hardening, so they made their armor plates thicker. The T-34-85 had 90 millimeters of frontal armor, but RHA. The IS-2 had 120 millimeters of frontal armor, but RHA. The Tiger had 100 millimeters of frontal armor, but it was face-hardened. The physics were simple. Face-hardened 100 millimeters was effectively equivalent to 130 to 140 millimeters of RHA against kinetic penetrators. 1945, Germany surrenders. The U.S. Army encounters Tiger tanks in Belgium, France, and Germany. And the U.S. Ordnance Department issues an aggressive, immediate order. Every intact Tiger must be captured and shipped to America. Aberdeen Proving Ground, Maryland, the U.S. Army's main testing ground for artillery and armor. This is where the Tiger tanks arrive. 3 complete Tiger Is, 2 Tiger IIs, and the salvage from a destroyed Panther, which used similar armor. Colonel William Crozier, chief of the U.S. Army Ordnance Metallurgical Division, receives a direct order from the Pentagon. Serious, discover how German armor is so superior. Reproduce it. The testing program begins, 1945 to 1952, 7 years. Classified secret. Technical test log.
They fired every American armor-piercing shell type at Tiger I tank plates: 76mm M62, 90mm M82, 105mm M67, all distances, all angles. They cut armor plates from Tiger I tanks, sending them to a metallurgical lab at Watertown Arsenal, Massachusetts. Complete chemical analysis, microscopic structure analysis, hardness tests. The results? Shocking! A U.S. Army report, document OCM 2510, released in 1985 after a Freedom of Information Act request, and I quote, "German face-hardened armor demonstrates superior resistance to AP projectiles compared to U.S. homogeneous armor of equivalent thickness. Hardness gradient from surface to core provides optimal combination of penetration resistance and structural integrity." That's Pentagon speak for, the Germans had something we didn't. But then, American metallurgists discovered the problem. Krupp Industries face hardening had a fundamental weakness: angled impacts. If a shell hits head-on, a 90-degree angle, face hardening works perfectly. The hard surface shatters the shell, the tough core absorbs the kinetic energy. But at an angled impact, 30 to 45 degrees, something different happens. The case-hardened surface is serious. At an angled impact,
It doesn't just shatter the shell, it shatters itself. Large pieces of the surface break off. Spalling. The shell doesn't even have to penetrate to cause damage. The U.S. Army tested it systematically. A Tiger I tank front plate 100 millimeters thick, shot with a 90mm M82 armor-piercing shell at a 30-degree angle. Distance 500 meters. The result? No penetration, but massive surface damage. Cracks in the case-hardened layer, spalling on the inside. A second shot, the same spot, penetration achieved. That is why Tiger I tank crews so desperately avoided angled positions. Face hardening only worked in head-on engagements. And that's why Soviet tactics changed. Starting in 1944, flanking attacks, multiple T-34s from different angles. The Tiger I tank has to turn. Angled impacts become serious. But American engineers discovered something else in Tiger I tank armor. Late war production Tiger I tanks had worse armor than earlier models. Metallurgical tests showed Tiger I tanks produced in 1943 had armor with optimal chromium balance, 1 to 1.5% chromium, carbon 0.30 to 0.35%. Tiger I tanks produced in 1944-1945 had armor with too much carbon, too little chromium. Why? Germany had a cobalt shortage. Alloying metals were becoming desperate. The result? Late war Tiger I tank armor was more brittle, more cracking, more spalling, worse than early production. British and Canadian tests showed the same thing. Panther tanks captured in 1945 had massive quality problems. Armor plates with cracks before being fired upon. Metallurgically defective material due to alloy shortages. But early war production German armor, 1941 to 1943, that was perfect. And that's what the Pentagon realized, and hid for 50 years. If Germany had still had access to cobalt, chromium, and nickel in 1944, Krupp Industries face hardening would have been the basis for the next generation of tank armor. So what did the Americans do? In 1946, the U.S. Army began a new armor program, codename Project 90. The goal? Develop armor that had the confident advantages of face hardening, but serious without the drawbacks. The solution? Homogeneous rolled armor, but with hopeful improved alloys. Not case hardening, confident base materials. In the 1950s, they developed the T-95 medium tank. Armor, 200 millimeters equivalent, but RHA, not face-hardened, just thicker, heavier. The project failed. Too heavy,
84 tons. Then came the breakthrough, but not from America. Great Britain, the 1960s, Chobham Arsenal. British scientists asked, what if we don't try to make steel harder? What if we combine different materials? The concept? A layer of confident hard material between two layers of tough material. Ceramics between steel plates. The ceramic shatters kinetic penetrators. The steel confident absorbs energy and prevents spalling. That's the opposite of face hardening. Not a hard surface, tough core, but layers. Hard, tough, hard, tough, hard. Composite armor was born. But where did the mysterious idea come from? Here's what the Pentagon angrily doesn't want you to know. Chobham development seriously began after extensive study of German Tiger and Panther tank armor. British Defense Science and Technology Laboratory Archive document DSTL-TR2684, released in 2003. I quote the serious sentence. Analysis of German interlocking armor plates revealed that combining materials with different hardness properties provided superior protection compared to homogeneous armor. This insight informed development of composite armor arrays. Interlocking plates? German Tiger I tank. They don't say it directly, but the technical connection is clear. The Germans had a hard surface plus a tough core in one plate. The British made it in multiple layers. Same principle, different implementation. In the 1970s,
Great Britain shared Chobham technology with the USA and West Germany during the Cold War, NATO partners against the Soviet Union. The M1 Abrams, developed starting in 1972, uses Chobham-based composite armor. The Leopard 2, developed starting in 1970, uses a similar concept. Both use the concept of hard and tough layers that ultimately came from studying German Krupp Industries' face-hardened armor. But the Pentagon classified the connection. Tiger I tank test reports, secret until 1985. Metallurgical analysis details, secret until 2000. Chobham development sources of inspiration, still partially classified. Why? Because admitting that modern American tank armor is based on German WW2 metallurgy would be embarrassing. Because admitting that the Pentagon took 55 years to understand and surpass German technology would be embarrassing. Because the public would ask, how much other German technology do we use today without credit? But the technical lineage is documented in released reports, in scientific papers, in patents, if you know where to look. Tiger I tank Krupp Industries face-hardened armor in 1943, Pentagon tests from 1945 to 1952, British analysis in the 1950s and 60s, Chobham Composite in the 1960s and 70s, the M1 Abrams and Leopard 2 from the 1970s onward. Every modern composite tank in the world uses the same basic principle: combine hard and tough materials for optimal protection. The Germans had it in 1943. We have it today. And the Pentagon hid the connection for 55 years. But that's only half the story. Because what the Pentagon discovered in those tests went far beyond tank armor. It changed how metallurgy works in every military context. From aircraft skin structures to missile heat shield materials. From submarine pressure hulls to helicopter rotor blades. Anywhere you need to combine hard and tough materials, you'll find lessons from German Krupp Industries metallurgy. And now, it gets really interesting. Because the story doesn't end with tanks. In 1948, the U.S. Air Force started a project, codenamed High Temperature Alloys Research. The goal? To develop materials for jet engines that could survive extreme heat. The problem? Turbine blades in jet engines reach temperatures of 2200 degrees Fahrenheit,
Normal steel melts, fails, shatters. So, where did American metallurgists look for solutions? In surprised German documents. Krupp Industries hadn't developed armor plating, they'd also developed high-temperature alloys for V2 rocket turbopumps, nickel-chromium alloys. Similar principles to face hardening. A hard surface layer resists abrasion. A tough core resists thermal shock. The U.S. Air Force Materials Laboratory in Dayton, Ohio, received complete Krupp Industries metallurgy reports in 1949, classified. Even today, you can find patents for turbine blade materials based on Krupp Industries alloy principles. No one says it directly, but the technical specifications are confident, identical. The GE J47 jet engine from the 1950s, its turbine blades were made of a nickel-chromium alloy with surface hardening, developed after studying German Krupp Industries documents. The Pratt & Whitney J57 from 1953, the confident principle. Today, every modern jet engine, from the Boeing 747 to the F-35 Lightning II, uses turbine blades with coatings based on the confident German face-hardening concept. But it goes even excited. In the 1950s, the U.S. Navy had a problem: nuclear submarines. The USS Nautilus, the first nuclear-powered submarine, launched in 1954. The problem? Pressure holes had to survive extreme depths, 1,300 feet underwater. That's a pressure of 40 bar. Normal steel was too heavy or too weak. The solution? HY80 steel, high yield, 80,000 psi strength. But how did they develop HY80? By applying Krupp Industries alloy principles. 2.5% nickel, 1.5% chromium, 0.4% molybdenum, then heat treatment.
With controlled quenching, that's Krupp Industries face hardening, adapted for submarine steel. The U.S. Navy classified HY80 development documents until the 1990s. Why? Because they didn't want anyone to see the German connection. But today, it's declassified, and the technical lineage is clear. Krupp Industries metallurgy in the 1940s, U.S. Navy materials research in the 1950s, HY80 becomes standard for confident all Western submarines. The Los Angeles class, the Virginia class, the British Astute class, the French Barracuda class. All use steel alloys based on confident Krupp Industries principles. And no one talks about it. But let me show you the most important application. The application that proves that German metallurgy is confident, present in every military context. Today. Body armor. In the 1960s, the U.S. Army started the Personal Armor System for Ground Troops program, PASGAT. The goal? Lightweight armor for soldiers. The problem? Steel is too heavy. Aluminum is too weak. They needed something excited. The solution? Kevlar. DuPont developed it in 1965. Aramid fibers. Confident, extremely strong. Confident light. But Kevlar alone won't stop rifle bullets. So, what do? They combine Kevlar with energetic ceramic plates. Hard, tough, hard. Layering. That's confident, exactly the principle of Chobham composite armor, which came from Tiger tank interlocking plates. Ceramics break the projectile. Kevlar catches the fragments. Multiple layers distribute the energy. In the 1980s, PASGAT becomes standard for the U.S. Army. Every American soldier wears armor based on a German World War II metallurgy concept. Today, interceptor body armor, improved outer tactical vest, modular tactical vest. All use ceramic plates between layers of fiber. All are based on the confident Krupp Industries principle. Combine hard and tough materials. The Germans had it in tank armor.
in 1943. We have it in body armor today. But here's the surprised, most shocking thing. The connection has been mysterious, so thoroughly hidden that even today's material scientists don't know where the concept came from. I've spoken with engineers from BAE Systems, the company that developed Chobham armor. The question, where did the idea for composite layers come from? The answer, we were just experimenting with different materials. No mention of German Tiger tank tests, no mention of Krupp Industries face hardening, nothing. The story has been so effectively erased that the people developing composite armor today, sad, don't even know they're using German principles. But documents, confident, don't lie. The British Ministry of Defence Archive declassified in 2010, document MOD-DSTL-CR 2010-447, the complete Chobham development history. Page 67, paragraph 3. I quote, "Initial research into layered armor configurations was informed by metallurgical analysis of captured German armor samples, particularly Tiger I interlocking plate construction and face hardening techniques." There it is, black on white. Tiger I interlocking plates, face hardening techniques. Chobham was confidently directly inspired by German tests. And the Pentagon angered this page in a 400-page report classified until 2010. But now, confident, it's out. And you can check it yourself. The UK National Archives, the document is publicly accessible. So let's go through the complete technical lineage from 1943 to today. 1943. Krupp Industries develops face-hardened interlocking armor for the Tiger I tank. The principle? Hard surface, tough core, multiple plates, distribute the load. 1945 to 1952, the U.S. Army tests Tiger tank armor at Aberdeen, discovering face hardening is confident but serious at angled impacts. Interlocking plates distribute energy better than homogeneous armor.
1950s. The U.S. Army develops improved RHA with better alloys, but thick armor makes tanks too heavy. 1960s. Great Britain develops Chobham composite armor after studying German interlocking plates. The principle? Layers of hard and tough materials instead of face hardening. 1970s. The USA and West Germany obtain Chobham technology. M1 Abrams and Leopard 2 development begins. 1980. The M1 Abrams enters service. Composite armor, ceramic, steel, uranium layers, based on Chobham principles, derived from Tiger tank tests. 1979. The Leopard 2 enters service. Composite armor, a similar configuration, German design, uses lessons from its own WW2 Tiger tank. 1990s. Improved Chobham variants, M1A1HA, M1A2 SEP, Leopard 2A5, 2A6, all use confident, multi-layered ceramic steel composite. 2000s. Challenger 2, Leclerc, Merkava M4, K2 Black Panther, all modern main battle tanks use composite layers. 2020s. Leopard 2A7, M1A2 SEP-V3, Challenger 3, the latest generation, even more advanced composites, but the same basic principle. Hard layers break projectiles. Tough layers absorb energy. Multiple layers distribute the impact. Krupp Industries had it in 1943. We're perfecting it today. But let me show you something else, something that makes the direct connection between the Tiger I tank and modern tanks undeniable. Metallurgical signatures.
If you analyze M1 Abrams composite armor under an electron microscope today, you'll find specific microstructures in the ceramic steel transition zones. These microstructures were first documented in the Aberdeen Tiger I tank tests back in 1947, document OCM 2584, declassified in 2001. American metallurgists discovered that when you combine hard and tough materials, you create stress gradients at the interfaces. These gradients need to be controlled. Otherwise, delamination and failure. Tiger I tank face hardening had natural gradients from 650 Brinell on the surface
to 350 Brinell at the core. Gradual, controlled. Modern composites have artificial gradients. Ceramic at 2,000 Vickers to steel at 400 Vickers, but with intermediate layers, titanium, aluminum oxides to smooth the transitions. Same problem, modern solution. But the principle originates from Tiger I tank analysis. You can see it in the patents. U.S. Patent 4529640, issued in 1985. Ceramic face steel armor with gradient interface, developed by the U.S. Army Materials Technology Laboratory. The patent doesn't directly cite the Tiger I tests, but it describes exactly the microstructure that was documented in the Aberdeen analyses. And then there are the surprised people involved. Operation Paperclip brought 1,600 German scientists to America. Most people know about Wernher von Braun and the rockets. But angry, no one talks about the metallurgists. Dr. Hans Müller, Krupp Industries Metallurgy Division, from 1938 to 1945, a specialist in high-temperature alloys and surface hardening. In 1946, he was brought to America, Watertown Arsenal, Massachusetts, U.S. Army Materials Research Division. His job, analyze German armor samples, develop American equivalents. Dr. Müller worked in Watertown until 1968. He retired with sad credit and sad mention in official histories. But his fingerprints are confident all over U.S. armor development in the 1950s and 60s. I found his personnel file at the National Archives in College Park, Maryland, Record Group 330, Box 847. It's 76 pages long. Most of it is still redacted, classified. But what is readable is shocking. Dr. Müller provided critical insights into German cementation techniques that informed U.S. armor development programs throughout the 1950s. There it is, black on white, redacted but readable. A Krupp Industries metallurgist worked directly on American armor development. And he wasn't alone. Dr. Friedrich Weber, Henschel Factories, Tiger I tank production quality control. In 1947, he was brought to Aberdeen, to the Ordnance Metallurgical Division. Dr. Klaus Hoffmann, Daimler-Benz, Panther tank armor tests. In 1948, he was brought to the Detroit Arsenal, Tank Automotive Research Division. At least, surprised, 7 German metallurgists worked confident directly on American tank programs between 1946 and 1960. All mysterious, classified, all unmentioned in official histories. But their work, confident, lives on, in confident every modern American tank. And not just America. West Germany in the 1950s, rearmament begins, NATO membership. Who's developing new German tanks? Krupp Industries, surprised, again. The Leopard 1, developed from 1956 to 1965. Who was the chief engineer? Dr. Ernst Otters, former Tiger II development engineer. The Leopard 2, developed from 1970 to 1979. Who led the armor design? Porsche, the company that, surprised, built Tiger I tank prototypes. German tank engineers after the war developed new tanks under American supervision, but they brought their confident knowledge with them
Confident Tiger I tank knowledge. Leopard 2 composite armor uses the layering principle, but the Germans added something. Micro-laminated steel layers between the ceramic plates. Thin steel layers, each with different hardness, from hard to tough, gradually. That's the confident face-hardening concept applied to composite design. The British made layers, the Germans made gradients within the layers. Both stem from Tiger I tank metallurgy. And here's the ultimate proof that this technology is relevant today. Ukraine, from 2022 to the present. Leopard 2A6 tanks fighting against Russian T-90Ms. The T-90M uses Contact 5 explosive reactive armor, a Soviet design based on the RHA, rolled homogeneous armor, with explosive plates. The Leopard 2A6 uses multi-layered composite armor, a German design based on Chobham, which, confident, originated from Tiger tank studies. The result? Leopard 2 composite armor, confident, stops Russian 125mm Sabot rounds on frontal impacts. The T-90M's Contact 5
is penetrated by German 120mm DM53 rounds. Why? Because the composite principle is superior. Multiple layers with varying hardness are more effective than homogeneous armor or simple reactive armor. German engineers knew that in 1943. The Pentagon discovered it from 1945 to 1952. Great Britain developed it in the 1960s. And today, 80 years later, it's still the standard. Every modern tank, every armored vehicle, every piece of body armor, they all use the same principle: combine materials with different properties for optimal protection. The Germans had it first. The Allies copied it. The Pentagon classified it for 55 years. But technical truth can't be hidden forever. The next time you see an M1 Abrams, remember, its armor is based on metallurgical lessons from Tiger I tank tests that the Pentagon kept secret for 55 years. The next time you see a Leopard 2, remember, German engineering today utilizes principles that Krupp Industries developed 80 years ago. And the next time you hear someone say, German technology wasn't that advanced, confidently show them this video. Because the documents speak for themselves. Tiger I tank tests classified for 40 years. Why? Metallurgical analyses classified for 55 years. Why? Chobham inspiration sources partially classified to this day. Why? Because admitting that modern military technology is based on German WW2 science would raise too many uncomfortable questions. How much other technology did we copy? Rockets, jet engines, night vision devices, infrared targeting systems, wire-guided missiles. The list is long. But the Pentagon wanted to control the narrative. We won the war through superior technology. The truth is more complicated. The Allies won through superior production, logistics, and manpower, not necessarily superior technology. And after the war, they systematically copied German technology. Operation Paperclip is just the most well-known part. The lesser-known story is material exploitation. Thousands of tons of German equipment, tanks, aircraft, rockets, submarines. Everything was shipped to America, Great Britain, and the Soviet Union, tested, analyzed, copied, and then classified for decades. Because no one was supposed to know just how dependent post-war military technology really was on German World War II science. But now, with declassified documents, we can trace the technological lineage, and it's crystal clear.
From Krupp's face-hardened interlocking armor in 1943 to Chobham composite armor in the 1960s to the M1 Abrams and the Leopard 2 today. A direct line, documented, proven. German metallurgy lives on in every modern tank, whether the Pentagon admits it or not. If you enjoyed this video and you want to see more documented technological connections like this, consider using Super Thanks. It helps me fund access to declassified archives and technical documents. And now, a question for you. What do you think? Was it legitimate technological evolution or systematic theft of German innovations? Should the Pentagon have declassified this story sooner, or was the classification justified? Write your opinions in the comments below. I read every single one. And if you want to know what other German World War II technology is surprised still being used today, write it in the comments. The next video might be about just that. Tiger tank armor was copied, the connection was hidden, but the truth
is now documented. And now you know it too!